Okay, chapter 9.2, composite bodies. Guys, the basic difference between chapter 9.1 and 9.2 is that in 9.1 we considered, just move that out the way, in 9.1 we considered continuous systems, right? So for example, if you had perhaps an area, we looked at that in the previous video, it's a continuous, and it's a kind of a complicated system, and it has this curve y equals x squared, or right, it had a continuous complicated volume or area or whatever, right? And so we needed to, in order to get the center, we needed to integrate, right? We needed to set up a little differential element, and we needed to use integration because we were using this kind of continuous system and integrating over a complicated continuous structure. Okay, so we use something like this, dA over dA, right? So there was a continuous system, and we first had to set up our differential area, our differential element, and we had to carry out this integration to solve the problem like that. But what if we can take a complicated structure, a complicated area, a complicated volume, whatever, and break it up into known geometries? Okay, so this is where we come to 9.2. So we take a complicated structure, and we break up that complicated structure into elements. Okay, so I don't know, say now we had a structure, right, looked like this, right? We've seen one. Well, actually we're going to do an example on that. So here we have a complicated structure. How do we determine the centroid? Well, we divide it into elements, okay? And then we carry out the same kind of equation, right? Remember, where does this come from? It's just the principle of moments, right? Principle of moments. But now we've got discrete, again, I discussed this in an earlier video, we've got discrete elements again. Whereas here we had these differential elements, right, that we were adding up, but now we've got discrete elements again. We've got two elements, and we carry out the same thing again. X is equal, but now because we've got discrete elements, we say the sum of xi ai over the sum of a, the sum of all the areas, or y, the location of the centroid in the y direction, y bar is the sum of yi over the total the area of each one over the sum of the areas. Okay, so just remember, when we have a continuous system, we need to use this because we're integrating, we're summing up all differential elements. But if we've got a structure like this, we can break it up into discrete elements or segments, right? And then we still carry this out, okay? So that's the basic idea. So that's where these equations come from. For this, we'll just focus. I don't know why it's not very good. Okay. It's most irritating, I have to tell you. Okay, there we go. So sorry about that. It's just poor equipment that I have. But here, for example, so a composite body, it says here, a composite body consists of a series of connected, simpler shaped bodies, which may be rectangular, triangular, semicircular, etc. Okay? So, and because we're working with connected, simpler shaped bodies, we use this equation here. You see there's no integral. There's the summation signs, meaning we're summing up discrete elements, okay? So here is an example. I'm not going to go through this example, but here you've got a complicated structure. All we need to do is break it up into simpler structures and apply this kind of equation here, okay? So I'm just going to do an example here of F9.8. Let's have a look at this F9.8. Very simple example, but hopefully it will illustrate the method we need to apply, Okay? So, let's get some space here. What we have, F9.8. F9.8, we have this structure that looks like this. And we are trying to determine the centroid, okay? But we're specifically trying to determine the y bar of the centroid, okay? And this is 0.15, 0.15, that the length's there. And this is 50 millimeters, okay? And this is the height from there to there is 0.3 meters, okay? And this, so if we go down the center like that, I mean, you can look at it in your textbook. This is 0.025, from there to there, from there to there is 0.025, okay? So what is our equation again? Taking moments, right? If we take that as our x axis and that is our y axis, then we know that because because of symmetry, the location of x bar will be perfectly somewhere along this y axis, right? Because it's x equals 0. Okay? So we don't have to worry about the x. We know that it's located somewhere along this line. All we're trying to find is the y bar, which is equal to the sum of yi area I divided by the total area. Okay? So all we're saying is that the moment of the total area about this x-axis is equal to the sum of the moments of all the areas about that same axis. So we have to divide this structure into two elements. There's element 1, there's element 2. And what we're after now, guys, is we're after the sum of this YA, and we're also after the sum of all the areas. So what we do is we set up a table, okay? We say segment, area, then we say YA, okay? So we don't need an X, we need it, and we need the Y tilde, okay? Remember, what is the Y tilde? The Y tilde, this is most frustrating, I'm sorry that there we go. Y tilde refers to the centroid of the element, okay? Or the segment, whatever you want to call it, okay? So we've got two segments, first segment, second segment, okay? We are basing everything upon this equation, which is simply a moment equation about this point here, okay? So what is the area of element 1? What is the area of element 1, okay? Because remember, we're trying to find the total areas. So what is the area of element 1? It's going to be 0.05 times, so it's 0.05 times 0.3. So we have 0.015 squared meters. What is the area of element 2? It is 50 millimeters times 0.3, which is also 0.015, okay? And the units here are meters squared. What is the y bar for each of these elements? Remember, the y tilde. This is the location of the centroid of each element. And in this case, it's a segment, okay? So what is the location of the centroid here? It's there, right in the center, because it is a perfect rectangle. So we need to go up this distance plus that distance. So that distance is 0.3, and that distance will be 50 millimeters divided by 2, right? So 50 millimeters divided by 2, 25 millimeters plus 300 millimeters equals 0.325 meters, okay? So it's going to go up there, plus that distance is 0.325 meters, okay? I hope you understand that. That's the y location of the centroid of segment 1. Now, what about this, the y location of the centroid of segment 2? It's just simply going to be half of that distance, which is 0.15 meters. Now, so that's great. We've gotten now the areas of each of the segments, and we've gotten the y locations of each of the segments. Now we need to multiply y times a, because that's what we get there. So what is y? So we just multiply these by each other, okay? So 0.015 times 0.325 equals 0.004875. We multiply that by each other. 0.015 times 0.15 is equal to 0.00225. Okay, now because we have to sum this up, we just get these totals. Okay, so we have 0.015 times 2, 0.03, and we add these two up and we get 0.004875 plus 0.00225 equals 0.007125. And plugging it into this equation, we get 0.007125 divided by 0.03. And that should be our y bar. 0.007125, 0.03 gives us 0.2375 meters, or 237.5 millimeters. Okay, so that is essentially, that's where our C is. Our y bar is there. Our y bar is 237.5 millimeters. So it's kind of makes sense to me. So there is this line there, which is now that point that gives us our centroid. So x bar will be 0 and y bar is 237.5, which is at that point. Okay, so what do? We have to first base everything upon this equation. And what do we want? We want the areas of each segment. First of all, we have to divide it up into appropriate segments. Then we need to calculate the areas of each segment, the y bars of each segment, and the ya of each segment. And then we plug it into this equation and we solve for the centroid. So the centroid is given by that. Thanks, guys. Cheers.